I didn't see you there. Well, since you're here, would you like to learn about the history of Chinese math? I knew you would. Chinese philosophy and intellectualism began around the 6th century BCE with the famous philosopher Confucius. But Chinese math didn't begin to flourish until the reign of Emperor Qin Shi Huangdi, sorry for my pronunciation, in 221 BCE. Under his leadership, he enforced a severe legal code, levied taxes evenly, and demanded the standardization of weights, measurements, money, and especially the written script, which made working with numbers and talking about them much more easy. However, the next dynasty in China was the Han Dynasty, which would last for about 400 years until 200 CE. And it was during this that the earliest Chinese mathematical text, called the Book of Numbers and Computations, was written. Also during this dynasty, there were two other books of math, called the Arithmetical Classic of the Gnomon and Circular Paths of Heaven, as well as the 9 chapters on the mathematical art. These last two texts that I mentioned, we don't have any copies of anymore, but we know about them from writings from other people who talked about them and even added on to them. We have some updated versions of specifically the second one, the 9 chapters. The first book that we do have mostly consists of problems and their solutions, not so much the theory of mathematics that goes behind it. After the Han Dynasty, China went through various periods of stability and instability. There were different dynasties, some governments kind of came and went. But throughout this time, since the Han Dynasty and into the 20th century, there were these entrance exams that were necessary for someone to become a civil servant. So no matter what government was in place, the tradition of this entrance exam existed. And while the entrance exam was mostly focused on literary classics and understanding literature and your ability to read, there were also some mathematical necessities within the function of government. Specifically, there was calendar making, tax collecting, and land surveying. So this meant that anybody taking these exams had to be familiar with some basic mathematical concepts. And this was a tradition, like I said, that lasted for a little over 2,000 years, very close to the modern era. From this tradition became the 10 mathematical classics. It is a collection of 10 mathematical textbooks from China that became widely circulated and widely used and kind of became a basis of mathematics. This includes the 3 that I mentioned earlier, as well as 7 other popular math textbooks. And then I said, not that kind of pie. Oh, hey, I didn't see you there. Would you like to learn some more about Chinese math? Well, you're in luck, because I've already got it written up on the board. We're going to talk about Chinese numbers, which are these right here. We've got, as you might guess, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Now, there is another form of these numbers in the textbook. Feel free to check them out. Chapter 7, Section 2. They are written pretty similar to this, slightly different. They function the same, so we're only going to cover the 1. Now, let's say you want to write a number larger than 9, say 26. You're just going to write the symbol for a 2 and the symbol for a 6. Let's say you wanted to write 206. Quite similar, you're going to write the number for the 2, you're going to leave a blank, and then you're going to write the number for a 6. And if you want to do a fraction, say 2 6, you're going to say 2. You're going to write the words Fenji, I believe pronounced Fenji, and then the 6. So that's going to be 2 over 6. If you want to do negative numbers, you're simply going to use a different color. I only have white chalk, so I can't demonstrate that, but say I had red chalk, a red 2 6 would be negative 26. Coming up next, we're going to talk about some math, some more advanced math that happens in, say, like the 1200s and later than that.
Man, I can't get the Game of Thrones theme song out of my head. Hey, what's up, guys? So another example of early advanced Chinese math, and specifically a technique, is the Chinese remainder theorem. So this was developed as early maybe as the 3rd century AD, and what it was relating a system of linear equations essentially in modular arithmetic. So if you know what a number is mod 2 and mod 7 in mod 17 or something, but you don't know what that number is, this is a method for finding what it is. And this is an example of one of the problems that they were asking at the time. So we have things of which we do not know the number. That's our number that we have to find. If we count them by threes, the remainder is 2. Okay, well, that's equal to 2 mod 3, right? Then if we count them by fives, the remainder is 3. And if we count them by sevens, the remainder is 2. Okay, well, we have these equations then. So n is congruent to 2 mod 3, like we said. N is congruent to 3 mod 5, like we said. And it's congruent to 2 mod 7. So this is just another example of like a common problem that would be asked of math students, and they had really good techniques for figuring out what the answers were. They're kind of formalized and then proven later on because they weren't too concerned with proving the things that they were using. It was more application based, but we won't go too far into the demonstration of how to use this theorem, but it's something that you should look up if you're either taking a math exam at like a high level that has number theory on it. So says Robert Krushner. One of the more impressive parts of Chinese math was the huge equations that they would solve. For instance, polynomials of degree 4 or even up to degree 10 with like crazy big coefficients. For instance, like 40 billion. And for instance, in specific, there was this one guy named Qin Jushao who was alive in the 1200s who would take huge equations like this and approximate, he would guess the answer and then figure out how far he was off by and narrow his answer down through a long and involved process. But nonetheless, pretty impressive that he could solve something this big. So what he would do essentially is he'd guess, in this case, he'd guess x minus 800 was the root. But he'd keep in mind, as he was doing this, that x is probably not really 800. It might be, but that's a pretty lucky guess if we're right. So he'd keep in mind that x is really 800 plus y. And what he would do is he would basically put this into the synthetic division method that we all know today. And he would divide the original polynomial by x minus 800 as if it really was a root. And then at the end of that, he would come out with some other polynomial and like kind of an error number. But the other polynomial would be in y. So this first step would be to determine how close his first guess was. And a lot of the time, what he would find is that his first guess was pretty close. He can get the first digit about right, and he can get the size about right. So for instance, this time he guessed correctly that it was one of the roots was in the 800s. Then he would be left with this polynomial in terms of y, and hopefully it'd be a little bit more manageable, but maybe not. And what he would do is the exact same thing, guessing at the first digit of y. So in this case, he guessed that it was 40. And what he found was that he was right the second time. Guy's probably a genius. I don't know. So in this case, he was able to find that one of the roots of this crazy equation right here, which, yeah, you're not seeing it wrong, that's 40 billion, is 840. But he didn't realize that there were up to 3 other roots of the polynomial. For instance, like, I don't think he would have even considered imaginary roots as a thing. He never really dealt with the negative roots either. So really to him, like, this was kind of, once you have the root x equals 840, you're done. So even though it really is impressive, he doesn't quite, it's not generalized. He He hasn't proved it as a theorem. He hasn't really proved it sufficiently yet. But what he's able to do is work with huge numbers and huge equations and actually get an answer out of it. So it's pretty cool. So then I was saying, like, if you have it equivalent to like 2 mod. Oh, yo.
Oh, hey guys, good to see you there. Thanks for watching our video. We really appreciate you taking the time. I know some of you didn't have a choice, but that's okay. We hope you learned some things about Chinese math, and you have anything to add?
Yeah, I mean, if you guys got any questions, just email our professor, Jed. He'll be happy to answer any questions you have, I'm sure.
Smart guy. Yeah.
Smart guy, yeah.
What's his email?
I think it's eherman@uwsp.edu.
Yeah, EHERMAN@uwsp.edu.
Yeah.
Happy to answer any questions that you have. Thanks.
Yeah, sure.
Thanks again, you guys. We really appreciate it.
Yeah, thanks.
Bye.
Thanks.
We'll see
Yeah,
you
okay.
We'll see you later.
See you next time, guys.
We really appreciate it.
Watch the next video. Like and subscribe if you can. Comments below.
Yeah, comments below.
Yeah, yeah.
Box
Dude, we should put in a box.
I don't know how to do that.
Still waiting, still waiting.
Sparkling sands of the diamond deserts.